Okay, beta, the recording of the meeting is on now. So let's now continue with our next topic of great circle sailing. So let me set up the presentation. This presentation takes us into the basics and calculation of great circle sailing. Now, before we go into how do we solve a great circle sailing question, we have to familiarize ourselves with the basic concept which are used in solving these type of problems. And those concepts, they come under spherical trigonometry. So we will be seeing some basic concepts of spherical trigonometry. Concepts will be one, the concept of a great circle and a small circle. Second, the concept of a spherical triangle. And third, we will be going into the formulas which we use in solving spherical trigonometry problems. There are two formula which we use. The first one is the cosine formula, and the second one is the Napier's rules. So this is what we are going to see in the basics of spherical trigonometry. Once we are clear about these basic concepts, it will be very easy for us to understand the working and solving of a great circle problem. So first we go into the concept of a great circle and a small circle. We have the diagram on the screen now. Now this is the diagram of a sphere. You can consider this sphere as the earth. The points at the top and bottom represent the two poles. You can see the North Pole where the pointer is right now. And the bottommost point you can see the South Pole. And exactly midway between them, this dotted line which you see is the equator. Now on a sphere or on the surface of Earth, a great circle is a circle on a sphere or on the surface of Earth whose plane passes through the center of the sphere. The great circle has the same diameter as the diameter of the sphere itself. The purple color circle which we see in the diagram is a great circle. So you see this purple color circle which we have in the diagram is a great circle because its plane, the plane of this purple circle, passes through the center of the sphere. The center of the sphere is represented by point C. So we can see that the plane of this circle passes through the center of the sphere. So this is a great circle. Now you can see the diameter or the radius of this great circle is going to be the same as the diameter and radius of the sphere. They will be exactly the same. Now, why is it called a great circle? Because this is the biggest diameter circle which we can draw or have on the surface of that particular sphere. It is not possible to draw a circle having a diameter greater than this that should lie on the sphere. So that is why it is called as a great circle. Now, as we have seen, the center of a great circle matches with the center of the sphere. To give you an example of a great circle, we have the equator on the surface of Earth. You can see the equator as a dotted line represented here in the diagram. So equator is a great circle. The plane of the equator passes through the center of the Earth, as well as the center of the equator is the same as the center of Earth. It is the biggest diameter circle which we can draw on the surface of Earth. So equator is a great circle. Also, like equator, all the meridians running from North Pole to the South Pole, all the meridians are great circles, or you can say parts of great circle. Now, a meridian and its anti-meridian or inferior meridian combined together forms a complete great circle. Like say, for example, if you consider the Greenwich meridian and the 180-degree meridian, if you join them together, it forms a complete great circle on the surface of the Earth. Now, we can only draw one and only one great circle passing from any 2 points on the surface of Earth. If you have two particular positions, 2 particular points on the surface of a sphere or Earth, there is only one and one great circle which passes through them. Now, there is one exception to this principle, this statement, this fundamental, and that is if these points are diametrically opposite. If these points are diametrically opposite, then we can have an infinite number of great circles passing through them. Like you have in the case of poles. The poles are diametrically opposite, so there can be infinite number of great circles that can pass. As an example, all the meridians 0 to 180 degree east and west are all great circles, and they are all passing from these 2 points, that is the North Pole and the South Pole. So 2 points which are diametrically opposite, infinite number of great circles can pass through them. And if we have 2 points or 2 positions which are not diametrically opposite, there will be one and only one great circle which will pass from both those points.
Beta, everything okay up to here? Any doubts in the mind? Okay, so I take it as all clear. So let's proceed ahead. We have seen a great circle. Now let's see a small circle.
Now moving on to the concept of a small circle. A small circle is a circle on the surface of a sphere whose plane does not pass from the center of the sphere. Like say, for example, the blue color circle which we see in the diagram, this one, this is a small circle because you can see the plane of this particular circle does not pass from the center of the sphere, which is at point C. So all these circles whose plane does not pass from the center of the sphere are called as small circles. The diameter or the radius of the small circle will be less than the diameter of the sphere. And the center of a small circle is not the center of the sphere. We know their centers are not matching. The centers of the blue small circle is here at this particular point, whereas the center of the sphere or the earth is at point C here. Now all the parallels of latitude except the equator are small circles. whether it is 10 degrees, 20, 30, 40, 50, north or south, all these parallels on the surface of Earth represent small circles because their plane does not pass from the center of Earth, and their radius is not equal to the radius of the Earth, and the center of these circles is not the same as the center of the Earth. So that was the concept of a great circle and a small circle.
Beta, all clear up to here? Any doubts?
No, sir.
Okay, very good. Let's proceed ahead.
Now we move on to the concept of a spherical triangle. We are familiar with plane triangles. We use them very often in our calculations. Now we are going to understand what is a spherical triangle. We have the diagram on the screen. A spherical triangle is a triangle on the surface of a sphere formed by the intersection of three great circles. Now, as you can see in this particular diagram, we have a triangle being formed on the surface of a sphere. This is a 3D diagram, and you can see this triangle being formed A, B, C. Now, this triangle is being formed on the surface of a sphere. That's number one requirement for a spherical triangle. And second, all the three sides of this triangle, you can see side AB, it is an arc of a great circle. The second side BC is also an arc of a great circle. And the third side AC is also an arc of a great circles.
Beta, just give me 2 minutes. I will be back. Okay, sorry beta, sorry for the interruption. There was a important call for tomorrow. Anyway, so we'll continue now about the spherical triangle. Any doubts till now, beta?
No, sir.
Okay, great.
All the three sides of the triangle should be the arcs of great circles. So that's a mandatory condition to be fulfilled for a spherical triangle. If any one of the sides is not the part of a great circle, or you can say if any one of the sides is the part or arc of a small circle, in that case, the triangle is not a spherical triangle. For a triangle to be called a spherical triangle, it is mandatory that all the three sides should be the arcs of great circles only. Now, in a triangle, there are total 6 components. There are 3 angles and 3 sides. In plane geometry, the angles are measured in degrees, whereas the sides are measured in units of length, that is meters, centimeters, millimeters, etc. But in spherical triangle, there is a difference, a significant difference. All these 6 parts, that is the 3 angles of the spherical triangle, like in this case, angle A, B, and C, as well as the 3 sides of the spherical triangle. You can see these 3 sides, AB, it is also represented as small c. Then BC, it can also be represented as small a. And the third side, AC, which can also be represented as small b. The side is either represented by the vertices which connect to form that side, like for this particular side, we can call it as AC, or you can also call it the small letter of the angle opposite to it. Now the angle opposite to this side is angle B. So you can also represent this side with small letter b. So in a spherical triangle, all these 6 parts, that is the 3 angles as well as the 3 sides, are measured in units of angles only. We do not measure the sides of the spherical triangle in units of length. They are all measured as angles. Now a doubt can arise in your mind that it is understood that angles are measured in angular units. So we can measure angle A, B, and C in the angular units of degrees and minutes. But how do we measure the side of a spherical triangle in degrees and minutes? Now to understand that, for easy understanding, the magnitude of the side of a spherical triangle is basically the angle subtended by it at the center of the sphere. So let's take, for example, side AB. You can see this is side AB. Now, if I join A with the center of the sphere here, and I join B with the center of the sphere, now both these lines joining A and B with the center of the sphere make an angle at the center. Now this angle is basically the measurement of this particular side of the spherical triangle. So repeating again, the magnitude of the side of a spherical triangle is the angle subtended by it at the center of the sphere.
So beta, this is also clear. Any doubts up to here?
No, sir. No, sir. Clear.
Okay, very good.
Okay, having understood the concept of a great circle, a small circle, and a spherical triangle. Now let's go into our first very important formula used in spherical trigonometry, that is the cosine formula. Now this formula is not only used for great circle sailing, but also used at many places in celestial navigation as well. So this is very important for the full navigation part. Now for this, let me make a rough diagram for a spherical triangle. You can see one side of the spherical triangle. Now we know all the sides of the spherical triangle are arcs of the great circle. So let me mark it as a GC. You can see the second side of the spherical triangle now in green color. This is also the arc of a great circle. Let's mark the third one now. You can see the third side of the spherical triangle, which is again an arc of a great circle. Let's give it a name also. Let's mark one of the vertices as P. Let's mark the second vertex as A and the third one as B. So Papa Alpha Bravo PAB triangle is a spherical triangle. That means it is made on the surface of a sphere, and all three sides of this triangle are arcs of great circles. Now the cosine formula says cos of any angle of a spherical triangle is equal to cos of opposite side minus cos of adjacent side 1 multiplied by cos of adjacent side 2 whole divided by sine of adjacent side 1 multiplied by sine of adjacent side 2. Now, what do we mean by the opposite side and the adjacent side? Let's try to understand. Let us consider any one angle of this triangle. Let's consider angle P. Now, you will see there are two sides of this triangle which are making this particular angle. In this case, angle P is being made by the side Papa Alpha, PA, and Papa Bravo, PB. Now these two sides which make this particular angle are known as adjacent sides. The third side, which is not in any way involved in making this angle, in our case, this is side AB, Alpha Bravo. This side is known as the opposite side. So this is how we explain the adjacent sides and the opposite sides. You can see that in this formula, the cosine formula, on the left-hand side, we can have any angle. In our case, angle Papa, angle Alpha, or angle Bravo. And on the right-hand side, you see all the terms are related to the sides of the triangle. So you have opposite side, then adjacent side, again adjacent side, and adjacent side in the denominator. So it tells us that if we have all the three sides of this triangle available to us, we can calculate any of the angles of this spherical triangle. Now let's try to understand the application of the formula for a particular angle. Let's consider angle P only. So we will try to apply this formula considering angle P.
Beta, can you Write down in your notebooks and tell me what will be the formula for cos of angle P.
Cos AB minus cos AP into cos PP upon sin AP into sin PB.
Okay, that was too fast. Slowly, beta, once again, one by one.
Cos AB minus cos AP into cos PB upon sin AP into sin PB.
Very good, beta. Very good. That's correct.
So the formula says cos of any angle. In our case, it will be angle P now. You can see this angle P marked here in the diagram. So the cosine formula, once applied to angle P, will give us cos of angle P is equal to cos of AB. You can see AB is the opposite side to this angle P, minus cos of PA. You can see PA is the first adjacent side, multiplied by cos of PB. You can see PB, Papa Bravo, is the second adjacent side to this particular angle, whole divided by sine of PA, that is adjacent side 1, multiplied by sine of PB, that is adjacent side 2. So cos of any angle is equal to cos of opposite side minus cos of adjacent side 1 multiplied by cos of adjacent side 2 whole divided by sine of adjacent side 1 multiplied by sine of adjacent side 2. So that is the application of the cosine formula. We can apply this to any of the angles as required by us, as we have done for angle P.
Okay, beta, now I would like all of you to write down this formula. Please note it down in your notebooks. You can note down the application for angle P also if you want. So this is a very important formula and we will be using it time and again. So you have to memorize it after writing it down. So just note it down and let me know when you are done.
Okay, sir.
Okay. Okay, beta. So let's proceed ahead now. We will now see how this cosine formula is used.
Now let's try to go a little deeper into the formula and try to understand what are the situations, scenarios, or questions in which this cosine formula can be used. There are specific conditions in which we can use the cosine formula. We have the spherical triangle rough diagram here, same Papa Alpha Bravo triangle. Now this cosine formula can be used in two conditions or two scenarios. What are these two conditions? Number one is when all the three sides of this spherical triangle are known to us. Papa Alpha, Papa Bravo, and Alpha Bravo, all three sides are known to us. Then we can apply this cosine formula and we can calculate all the remaining angles of this triangle. Angle Papa, angle Alpha, angle Bravo, all three can be easily calculated. We just saw in the formula itself, on the right hand side, we have all the sides. So having all the sides known to us, any of the angles can be found out. Now the second condition or scenario in which cosine formula can be applied is when we know any two sides of the spherical triangle and very, very important, included angle known to us. What do we mean by the included angle? If any two sides of this triangle are known to us, let us say we know Papa Alpha, the green color side of the triangle. We know Papa Bravo, that is the blue color side of the triangle, and the included angle. The included angle between these two sides is the angle P, angle Papa. So in this case also, two sides known to us and the included angle known to us, cosine formula can be applied. Now when we apply the cosine formula, the first thing which we will be able to calculate or find out in this triangle is the missing side, the unknown side. In this case, the side AB, Alpha Bravo. Now once the missing side has been known, has been calculated, then we again have access to all the three sides of the triangle, and the remaining two angles, that is angle alpha and angle bravo, can also be calculated and found out. Now, important thing to understand here is that the angle which you know should always be the included angle. If you know an angle other than the included angle, then in that case, cosine formula will not be applicable. So to give you an example, if you know side PA, the green color side, and side PB, the blue color side, and you know angle A. So in this case, angle A is not the included angle, and we will not be able to use the cosine formula here. Again, if angle B is known, same thing happens. Angle B is not the included angle, and we will not be able to use the cosine formula here. So it is very important that we know the two sides, any two sides of the triangle, and the included angle for the cosine formula application. Now a doubt may arise in your mind that in case we have two sides and an angle which is not the included angle, how to proceed ahead and solve that triangle. So in that case, we can use, or we have different methods with which it can be solved, but they are not required right now as far as the great circle problem is concerned. So we will see what is to be done when we come to those questions. For now, we will always have one of these two scenarios. Number one, when all the three sides are known to us, and number two, when any two sides and the included angle is known to us.
Beta, any doubt up to here?
No, sir.
Okay, so with this beta, we have basically covered up the spherical trigonometry concepts which were required to do or solve a great circle question. Proceeding forward, now we will be moving on to the stepwise solution of the great circle problem. How to calculate the great circle distance, how to calculate the initial and final courses. So shall we start that off in the tomorrow's class?
Yes, sir. Tomorrow will be better.
Yes, sir.
Yeah, I have a class with you in the morning.
Yes,
so
sir.
yeah, we have understood the basic concepts, and we can move on to the solution, because once I start off with the solution, it is going to take some time. We need some continuity. So we'll do it tomorrow morning.
Okay, sir.
Yes, sir.
Thank you.
Okay. So then we call it off for today. You can log off then for today, and I'll see you tomorrow with the great circle
Good night.
problems.
Thank you, sir.
Okay, beta. See you. Thank you. Bye bye.
Thank you, sir. Thank you, sir.
Thank you, beta.